So since it's lecture number 3, and I figure I should do a recap to make sure that that we, myself included, still remember what happened in the first lecture. Does that make sense? Is that okay? So just as a quick recap, so we have a finite signal, so a map from Z and D to C. I'm not going to go through all the slides, of course. Just, I'm going to hit basic points. Okay, and so we transmit the Fourier transform with L2 normalization, and so there's Fourier inversion. So if the whole signal is transmitted, if all of the Fourier transform is transmitted, then you can take the inverse Fourier transform, which is a very efficient operation, and you can get the signal back. So the basic question that we are asking is, can we recover F exactly if some frequencies are lost? Okay? And if some frequencies are lost. I also want to make a point that I sort of made in passing, but I want to make it explicit. So one of the things that Zita Maeli and I tried to do in this project is to kind of unify random results and deterministic results. So it is actually of interest to consider a situation, apparently, where the frequencies in the sphere are missing. I was told that this even has practical applications. Just that I'm not going to say this with an air of authority because I don't like to BS. Okay, but apparently this is the case. And also there are results of practical interest where random frequencies are missing. Okay, and the unification mechanism is restriction theory, which can handle both. Okay, so if I had to describe this whole lecture series, at least up to the end of today's lecture, tomorrow I'm going to talk about continuous results. This would be the recap. But let's go over a few basic points. So yes, we can recover the signal if some Fourier frequencies are missing, if the size of the support of the function or the signal times the size of the missing frequencies is less than n to the d over 2, and this is an application of the classical uncertainty principle. Okay? So there are some direct mechanisms which can be used in special cases, but let me just very quickly remind you what happens. Go straight to the Matolcsi, Szuchs, Donoho, Stark point of view. So the way it works is, suppose that you send a signal and some frequencies are missing. What does it mean that you cannot recover them? It means that there exists another signal G with support of the same size, so that the Fourier transforms agree except on the missing frequencies, of course. So you subtract G from F, you notice that the size of its space support is no more than twice the support of F. You notice that its Fourier support is contained in the set of missing frequencies. You apply the uncertainty principle, assume the opposite, and you have unique recovery. Okay, so this is the basic idea. And so this method works for any sort of a signal, and it cannot be improved in the case where you are so unfortunate as to have a signal supported, which is, say, an indicator of a k-dimensional subspace, because the Fourier transform is essentially indicator of the perpendicular plane, and the Fourier uncertainty principle is shown. However, this situation very, very seldom arises, and this is where restriction theorem is used to expose the fact that this situation almost never arises. Yes, please.
But this asks for how it's called, I forgot, stability theories. So if you are close to MD over 2, then you should be structured on this hyperplane or something.
I'm very glad that you said this, because theorems like this are extremely difficult. And the way we attempted, and I think partially succeeded in getting away from this difficulty, is by proving that if you have any sort of a restriction estimate, a trivial restriction estimate, that you can't possibly be close to one of these bad examples. And then we also prove that in vast majority of cases, you do have this restriction estimates, which means that the bad cases that you described don't happen very often. But we don't do this by showing this directly, but rather by using restriction theorem and showing this indirectly. But yeah, that's exactly the point. We know what the sharp examples are, but we don't know what the quasi-extremals are.
Because if S was a subspace, there is no chance for a restriction theorem.
None. But so that part is clear. What is less clear is how many sets are there for which maybe you don't get the worst possible uncertainty principle, but something close, up to a log, up to a constant, etc. And we didn't address this head on because that's an extremely, classification questions of this type are notoriously difficult. So we got around it by proving that if you have a restriction estimate, non-trivial restriction estimate, then this situation doesn't arise. And then we also prove that this non-trivial restriction estimate holds in the vast majority of situations. That's the strategy. Okay, and please. Oh, sorry, I didn't see.
Well, maybe you could actually go to some stability results. You have restriction estimates depending on additive energy and stuff. So maybe can you use the approximate subgroup theory, things of this nature, to say that okay, if your restriction estimate is bad, so you have low additive energy and then you're close to a subspace.
This is a wonderful idea. In other words, your point is that having established this point of view, maybe we can circle back and say something about the stability results. To be honest, it simply didn't occur to me. This is a very nice idea, right? Because the whole point was to get away from this, but that question is interesting in itself. So now by using these restriction estimates, maybe one can go back and say something. Now that I think about it, actually this is very exciting. I can't drop everything and go and compute because I have to give a talk, but it must be possible, right? Because it all somehow connects, right? And I would love to discuss this more. No, I seriously didn't think of it. All right, so once again, the theme that occurs in many different disguises, in many variations, is that the classical uncertainty principle that is almost never shown. And one of the manifestations was the additive energy uncertainty principle, where we define additive energy in the usual way, the sum of additive quadruplets. And the result says, it's a quantitative result, that says that the moment your additive energy is better than trivial, you get a better uncertainty principle. And there are two versions. One version involves a somewhat unfortunate quantity where you have to compute additive energy over all the subsets of the set of missing frequencies. But there's another version that we discussed. Where is it? No, it's a bit later. Another version that, yes, where all one needs to know is the additive energy of the support of the function and additive energy of the support of the Fourier transform. So in that case, any improvement over the trivial estimate gives you a better uncertainty principle. Okay? And another point that I feel that is very important that we went over is the fact that every restriction estimate carries in a very powerful way, every non-trivial restriction estimate carries an uncertainty principle mechanism that is built in. And the best way to see it is from the duo of the restriction estimate, the so-called extension estimate, which I think is even better expressed in terms of lambda Q sets. Okay, and the version of Bourgain's lambda Q set theorem that was used is the following: you have a signal from Z and D to C, and the Fourier transform is supported in S. Then if S is a generic set of size approximately n to the 2D over Q, then the weighted LQ norm Q is always bigger than 2. Then for a weighted LQ norm of F is bounded by a constant times the weighted L2 norm, where the constant is independent of N. Okay? So this is the celebrated result by Bourgain, and it carries a very simple but very powerful mechanism, which
And the constant doesn't depend on dimension N.
the constant is the constant independent of D. It's certainly,
Independent of D. That's what I wanted to ask.
I fear that it might be. This is one of many questions that are being, so I have these students that are suffering through Bourgain's paper, and this is one of the questions. It's not immediately obvious. Yeah, so I don't want to make assertions. Maybe it's just pessimism that comes with age, but I suspect that it does. Yeah, I think that one would have to work. Now the question is, can you remove that dependence? But that's a separate, I suspect. Anyway, so I will know more. Okay, so the uncertainty mechanism that's built into to Bourgain's result is that if you take a generic set of size approximately n to the 2d over q, and the Fourier transform of a function is supported in this set, then support of the function is a positive proportion of the whole space. And the constant in this positive proportion is just the reciprocal of Bourgain's constant raised to the power of 1 over 1/2 minus 1 over q. Another thing that I mentioned, I was racing to have this ready for this lecture series, but it's not quite done. But this will be a paper with Mayeli, Kashin, and Limonova, where we handled sets roughly of size n over log n, or n to the d over log to the alpha n. And this is partly based on a version of Bourgain's result by Kashin and Limonova, where they handle ordered spaces above L2. This is the most difficult case. So ordered spaces above LP, where P is bigger than 2, were previously handled by my former student, Donoho. But when P equals 2, this is especially difficult. Okay. All right. So another set of results that we started going over, and this is what most of today's lecture is going to be about, are the annihilating pairs inequalities. So in one dimension, this is a result due to Nazarov, where in one variable he proved that the L2 norm of the function f is bounded by e to the power of constant times the measure of e times the measure of s, times the L2 norm of f outside of e plus L2 norm of the Fourier transform outside of s. During the lecture, I erroneously said that there was a higher dimensional version of this established, and Maud pointed out that this is not the case. These results are much harder in higher dimensions, and one can only prove it under additional assumptions. And in the discrete setting, Gober and Jaman proved the following result, that if you have E and S are subsets of Z and D, and the size of E times the size of S is less than n to the d, so the opposite of the classical uncertainty principle condition. But please note that E and S are arbitrary sets here. Okay? Then the L2 norm of F is bounded by a constant, which is written out, times again the L2 norm of F outside of E, plus L2 norm of the Fourier transform outside of S. And this, of course, easily implies, there's a variety of applications of this, some of which I'm going to mention, but in particular, this implies the classical uncertainty principle instantly, because if you assume that F is supported in E and the Fourier transform is supported in S, then the right-hand side is 0, and so is the left-hand side. Moreover, it is clear from this that if you merely assume that F is concentrated in E and the Fourier transform is concentrated in S, then you still get a suitable version of the uncertainty principle. So I think that the annihilating pairs inequalities is really one of the nicest ways of encapsulating the uncertainty principle. And so I went through the proof of Gobert-Gemung last time. This is where I stopped. And so, so the idea is that the version of the annihilating pairs inequalities by Gobert and Gemung that I just stated works for all possible sets E and S. So given what we've already heard, it is reasonable to suppose that if E and S satisfy additional hypotheses. In other words, in the generic case, we should be able to do much better, and this is what we are about to see. Okay. So this is a recent result, which is joint work with Philippe Gemung and Asita Mayeli. We did a lot of work at the Cambridge Institute, but the memory that I will carry with me forever is I asked Philippe Gemung, who is French, what he wants for dinner, and he says that he doesn't want to eat in England, he will eat when he gets back home. That was cute. Okay. So, anyway, so suppose that a PQ Fourier restriction estimate holds for S in Z and D, and P is between 1 and 2, and Q is above 2, with norm CPQ. Then we have the same result, but this time the constant reflects the fact that we have a less stringent condition. Namely, instead of the size of E times the size of S being smaller than n to the d, it is enough to have the size of E to the 2 minus P over P times the size of S is less than n to the d over CPQ squared. And as I never get tired of saying, because I had to get used to this when I started working in the discrete setting, the constants matter. Right? So for this to be meaningful, the constant has to be manageable, and you should think of n as an asymptotic quantity. Okay? And so when P and Q are between 1 and 2, there is the following nastier version of this. Okay? And the reason I'm telling you about this version of the inequality for 2 reasons. One is for the sake of completeness, because P and Q is not obligated to be bigger than 2. That's one reason. But the second reason is that to prove this inequality, you can't purely use Hilbert space methods. You have to use Hausdorff-Young inequality, okay, in the discrete setting. And even though I'm not going to go into this today, what the best constant is in the discrete setting would certainly be interesting to know. There is a paper on this topic, but I was not quite able to deduce from that paper whether the exact constant is known in all situations. And I haven't yet decided whether it's my fault or the fault of the others.
Yeah. Yes. Can you do this by going from F to F hat? No, probably not.
No, I think it's a little hard. Okay. So this is the version between P and Q, and the exponents are ugly. The only thing that I want you to notice about these exponents is that it's considerably better than the classical uncertainty principle. In fact, this power over here is smaller than 1 over P. Okay. So this is the version when P and Q are between 1 and 2. Okay. So let me go ahead and go through the first result with Gemung and Mayeli, and let me remind you what it says. Oh, there you go. So this is where the L2 norm is, again, bounded by the constant times the usual quantity, L2 norm of F outside of E plus L2 norm of the Fourier transform outside of S. And in these types of results, the constant is of the form 1 plus 1 over the quantity. And here you have 1 minus. And the point is this quantity needs to be positive, which leads to that condition below. Okay? So let's go ahead and go through the proof. The proof is not that difficult, but I think it's kind of instructive. So, so let's first handle the case when Q is above 2. Okay? So we applied the restriction assumption. So we pull out the size of S to the 1/2, because in the restriction inequality, we have a weighted L2 norm. And so if we have an LPOQ restriction hypothesis, so the weighted L2 norm is bounded above by the weighted LQ norm. And then we apply the restriction inequality. We get the size of S to the 1/2, the norm, n to the minus d over 2, and the LP norm of F. Okay? So now we apply the Holder inequality to bootstrap LP back to L2, because we need a common frame of reference. This becomes a bit more of a technical issue if one wants a purely LP interrelation pairs inequality, and we'll get to that later. Okay, so by Holder's inequality, we bound this by this quantity square root of CPQ squared, the size of S, size of e to the 2 minus p over n to the d, times the L2 norm of e. Okay? So what we did here is we localized F to E by brute force, and we estimated the L2 norm on S. But ultimately, we want the L2 norm on the whole space, which tells us that we need to know something about the L2 norm on S complement. So we compute the L2 norm on S complement of the Fourier transform of the indicator function of E, and we just bound it from below by the triangle inequality by the L2 norm over the whole space minus the L2 norm over S. And and so this is greater than or equal to. For the first inequality, we simply apply Poincaré. And for the second one, we apply the upper bound we just obtained. Of course, you can only do this if this quantity is not negative. Okay, so now we are basically ready to finish up the proof. So we bound the L2 norm of the function by the L2 norm over E plus L2 norm over E complement. And this is why we unified the norms. Because now we can apply this inequality in reverse. But on the other side, we have L2 of S complement norm of 1EF hat, which is not quite what we want. We want the L2 of S complement norm of F hat. Okay? So what do? We unravel the quantity 1EF hat L2 of S complement. So how do we do that? We simply write it as, so we have S complement as F hat minus 1E complement F hat. Here we just apply the triangle inequality. The minus doesn't help us. So we get the L2 of S complement norm of F hat. This is good because this is what we are aiming for. Plus L2 norm of F on L2 of E complement. And now we simply feed this back into the inequality and establish the result. Okay. So one of the things, hopefully, I'll be able to get across in tomorrow's lecture is how much uglier all of this becomes when you have to operate in Euclidean space and worry about the fact that the Fourier transform of a rectangle is not exactly a rectangle. All right. So now let's prove the result when P and Q are between 1 and 2. Okay. So by assumption, once again, we have the LQ norm of 1EF hat. So once again, we force F onto E by multiplying by the indicator function, right? We have to take out the size of S to the 1 over Q because it's a normalized LQ norm. And then CPQ is the norm, n to the minus d over 2. This is just a factor in the definition of the restriction inequality. And then LP of E norm of F. Okay? And this we map up to L2 again. So we've seen this movie before. We map it up to L2. And this, by Holder's inequality, produces a factor of the size of E to the 1 over P minus a half. And then you have the norm, n to the minus d over 2, L2 norm of E. Okay? But now we're out of luck. We can't run the same tricks as before because we are below L2. since we're below L2, we run Hausdorff-Young inequality. So here, for the purposes of these lectures, I simply did not address the point of the best constant here, okay? So just by following the straightforward knuckle-dragging interpolation between L1 and L infinity and L2 and L2, you get Hausdorff-Young as always, okay? So on L2, you have a constant 1. On L infinity, you have a constant n to the minus d over 2. You interpolate using convexity, and this is what you get. Okay? So how do we use this? So using Hausdorff-Young, so remember the Q norm is below 2. So what we do is we apply Hausdorff-Young to the indicator function of EF Fourier transform, but we bound it from below. So we apply Hausdorff-Young in reverse. And that's bounded from below by n to the d over 2 minus q over q times the LQ prime norm of E. Okay? And we are now above L2. I always breathe easier when I'm above L2. And I truly get scared when people talk about LP for P less than 1, but that's a separate conversation. Okay? And this is bounded from below. Now we map down into L2. So n to the d over 2 minus q over q. Then you have the size of E to the 1/2 minus 1 over q prime. And now we have an L2 of E norm of F. So we map down into L2. Okay? So combining, we see that we can bound the L2 of E norm of F by the LQ of S complement norm of 1 EF hat divided by the difference of the two quantities that we just obtained. Okay? So I'm fully aware of the fact that there are now ugly formulas flashing before you, and I'm going to try to elucidate them the best I can. So please feel free to stop me at any point. Okay? And so now we again need to unravel 1 EF hat of LQ of S complement, but we've seen this movie before. Okay, we simply write it as the LQ of S complement norm of F hat minus 1 E complement of F hat. And we bound this as before by the LQ of S complement norm of F hat and 1 E complement F hat norm of LQ of S complement. And this we bound by the size of S complement to the power of 1 over q minus 1/2 times the Fourier transform L2 of S complement and L2 of E complement norm of F. Okay? Now, as always, we bound the L2 norm by the L2 norm of E plus the L2 norm of E complement. And rearranging the terms yields the conclusion in the case P less than Q between 1 and 2. So the only thing, so the biggest thing I would like for you to get out of this is that Hausdorff-Young inequality is used as a mechanism that we use to rescue ourselves from the hell that is LP spaces between 1 and 2. Okay? That allows us to pull ourselves back to above L2, and then we're able to use the same or similar methods as before. And as I mentioned, one of the things that would be highly interesting to know is what are the best constants in Z and D for the Hausdorff-Young. This is simply didn't look into carefully. All right, so another object that came up when we were discussing restriction theory, or when we were discussing improving uncertainty principle in the presence of extra structure, is additive energy. Okay? And here is a version of additive energy annihilation inequality. This is again joint work with Philippe Germain and Zita Maeli. And here the assumption that we make is instead of assuming that the size of E times the size of S is less than n to the d, we assume that the maximum over subsets of S of the energy of U over the size of U squared times the size of E is less than n to the d. that first term is never larger than the size of S. Therefore, this can only improve the classical condition. Okay? And then once again, we get that the L2 norm of the function is bounded by what we call the annihilation constant times the L2 of E complement norm of F plus L2 of S complement norm of F hat. And the constant reflects the fact that the maximum of lambda u over size of u squared times the size of E is less than n to the d. You can essentially predict what the constants are going to be in these inequalities from that point of view. Okay. So how is this proved? This is instant. This is proved by taking the universal restriction theorem. Let me maybe go back and remind you what the universal restriction theorem says. If I were clever, I would have just copied it on that slide. If I were that clever, my whole life would be simple. Yeah, there's universal. So there's the universal restriction. Yeah. So it says that you have an L4 thirds to L2 restriction estimate where the constant is bounded by the ratio of the size of S to n to the d over 2 raised to the power of minus a half times that quantity that's been arising over and over, energy of u over u squared, max over u and S to the power of 1/4. It's universal in the sense that this estimate always holds. It's just not always good, but it always holds. Okay? So let's go back. Around here somewhere. And, yeah, there we go. So the additive energy annihilation inequality simply comes from taking this constant from the universal restriction theorem and putting it in place of the constant C4 thirds 2 in the restriction annihilation inequality, right? We have an inequality where you're given the restriction theorem and you get an annihilation inequality. You simply insert this term in there and you're done. Okay? And as we discussed, it was not yesterday, it was on Tuesday, this is by no means the only universal restriction theorem one can prove. It's just the one that's easiest to visually observe, so I chose to go with this one. Okay? And similar results can be obtained in Euclidean space, and you're going to see some of them. Okay, once again, we can symmetrize. So the result you just saw uses additive structure of the set S. You can similarly take advantage of the additive structure of the set E, and in fact, you can take advantage of both by simply taking a convex combination. Okay? And, right, so we simply take these two inequalities, insert them, use the universal restriction theorem by reversing the roles of F and F hat, and obtain this result. Okay, so another question that arose on Tuesday is, can one prove a purely LP version of the annihilating pairs inequality? And it depends on what you mean. I claim that it is not reasonable to expect an LP version where you have the same LP space hitting the function and the Fourier transform. That's just not reasonable to expect. Okay? So here's the version that we are able to prove. So we assume that the size of E to the 2 minus P times the size of S is less than n to the d over CPQ to the power of P. So P is between 1 and 2. One can prove versions of this as well. Then the LP prime norm of F is bounded by a constant, we'll discuss it in a moment, times the LP norm on S complement, plus another constant times the LP prime norm of E complement. So in other words, the P prime on the left-hand side matches the P prime on the norm of the function. But the Fourier transform is hit with the dual norm. And I suspect that nobody in the audience is shocked by this. Okay? And since the 1Q restriction theorem always holds with C1Q equals 1, then for any sets E and S, so that the size of E times the size of S is less than n to the D, here we make no assumptions. Okay? Then the L infinity norm of F is bounded by this constant, which is rather small, times the L1 norm of the Fourier transform, plus another constant, which is the same constant that arises in the classical annihilation inequality, times the L infinity norm of F. Okay? So in particular, if the Fourier transform is supported in S, then this first term disappears, and what we have is an L infinity concentration inequality. It says that the Fourier transform, the L infinity norm is concentrated in the complement of any set satisfying this basic condition. So we've seen the L2 version of this, but now we get the L infinity version of this using this LP annihilation pairs inequality. Okay? So I know that today's lecture is rather technical. Tomorrow we'll go back to, I think, more exciting things. So occasionally one has to do technical things in this business. It's terrible. Okay. All right, so let me just quickly run through the proof. Actually, it's not entirely true. We are going to do some fun things because we'll talk about the arithmetic manifestations of these things in a few minutes. Okay, so what is the proof? So you take the PQ restriction bound. So you bound the LP norm of 1E F hat. Once again, we force F onto E by the size of S to the 1 over P times the LQ, weighted LQ norm of the restriction operator. Okay? So we are assuming the restriction bound. So we bound it by CPQ n to the minus D over 2, the size of S to the 1 over P, times the LP norm of F. Okay? And this brings us up to CPQ n to the minus D over 2. So we are going up from LP to LP prime. For the same reason as always. We never, in these sorts of calculations, we never want to get stuck below 2. Okay? So we map up from LP to LP prime, and the price that we pay is the size of E raised to the power of 2 minus P over P. So then on the other hand, it's the same style as before. We bound the LP of S complement norm of 1E F hat by the triangle inequality, by the LP norm of 1E F hat on the whole space minus the 1E F hat on LP of S. Okay? And here, for the first term, we bound it below using Hausdorff-Young once again. Okay, so this is Hausdorff-Young. Right? Since we're going for for a Banach space bound, not a Hilbert space bound, Hausdorff-Young had to be used. This is all we have here. Okay? And then for the second term, we use the upper bound that we just obtained by using two tricks. One is the, well, not tricks, two concepts. One is the restriction theorem, and the other one is simply cheaply mapping from LP to LP prime. Okay? And we combined the terms. And as I said, in the second line, we used the Hausdorff-Young. Now, once again, LP of S complement norm, we simply write as the LP of S complement norm of F hat minus 1E complement F hat. We bound it up by the triangle inequality, by the LP of S complement norm of the Fourier transform, plus 1E complement F hat of LP of S complement. And here, the first term we already like, there are no issues. And the second term, we normalize, right? We take out the size of S complement to the power of 1 over B. And inside, we divide by S complement. Here, I'm probably being excessively cute because in a typical situation, the size of S complement will be very close to n to the d. So I could have just done that, but who knows when this might come in handy. Okay, so we normalize it this way. And so this is bounded by, again, the LP of S complement norm of F hat. And here we map up to LP prime, right? So here this is LP. We once again map up to LP prime. We go above 2. And for this, we paid the price of the size of S complement, 1 over P minus 1 over P prime. Okay, and now we have just a pure LP prime norm over the S complement. The first term simply comes down, and for the second term, we use Hausdorff-Young yet again. Okay, so Hausdorff-Young had to be used twice here, and this is not inefficiency. This, in both cases, it was fundamentally needed. Okay? And that this gives us LP of S complement norm of F hat plus n to the d 1 over p minus 1/2 familiar quantity times the LP norm of P complement. Then by the triangle inequality, we bound LP prime norm by LP prime norm of E plus LP prime norm of E complement. And now we simply combine the terms that we have. So we get this quantity, then we unravel this quantity, which we just did a moment ago, and we arrive at the quantity that was claimed. Okay. So algebra at the end is very, very nasty. I had to use my usual principle of when I get the same answer 3 times in a row, then it's correct. That's before.
Usually 2 is enough.
Not for me. See, I got into mathematics late, so I have to do it 3 times. It's not as natural for me. Okay. All right, so this is the, so again, the point is that an LP annihilating inequality is possible, but the price that you have to pay is you have to use, first of all, you don't have the same norm on the function that's Fourier transform, that's natural. You have to use Hausdorff-Young twice, and you need some kind of a restriction estimate, non-trivial restriction estimate, to get LP other than P equals 1. In general, you do get an L1, L infinity version, which is not implied. I checked this very carefully. It's not implied by the Hilbert space version. Okay? Okay, so let's see. So now I'm going to, 1 second. Yeah. So before I move on, so there are a few more things to clean up. So let's go back to the first result. First result, which is the Hilbert space result. Okay. And, right. So this result, once again, easily implies the uncertainty principle, right? And which uncertainty principle does it imply? It implies the uncertainty principle that Azitomayev and I obtained earlier that year by different methods. So let me show you one of this. So once again, you have F mapping Z and D to C. It's supported in E. Fourier transform is supported in S. Suppose that S satisfies a PQ restriction estimate with norm CPQ. Then if it should say here that Q is above 2. So P is less than or equal to 2, Q is bigger than or equal to 2. Then if the size of E to the 2 minus P over P times the size of S is bigger than or equal to n to the D over CPQ squared, okay? No, if Q is bigger than or equal to 2, then the size of E to the 2 minus P over P times the size of S is bigger than or equal to n to the D over CPQ squared. And if P and Q are between 1 and 2, then you get the same numerology as you saw in the annihilation inequality. Now, remember, in the second lecture, I proved that if a restriction estimate is satisfied, and if e to the 1 over p times the size of s is bigger than or equal to n to the d over the norm of the operator, well, it's bigger than or equal to the norm of the operator. I don't know why I keep saying if. Okay? But this estimate is stronger because 2 minus p over p is less than 1 over p. Okay? And another point that I want to mention in passing is that the original version of the uncertainty principle based on restriction cannot be used to deduce that consequence that we got from Bourgain's theorem, right? So Bourgain's result implies that if you have a set of generic size, or if Bourgain's inequality holds, then if Fourier transform is supported in S, then F is supported in a positive proportion of the whole space. But this version of the uncertainty principle based on restriction is strong enough. So this is the one that matches up with Bourgain's estimate. In other words, assuming that the restriction holds and deducing this consequence gives you the same consequence as Bourgain's result. So based on this, you can in the same way show that if the restriction estimate holds, and if the Fourier transform is supported in S, then the function is supported in a positive proportion of the whole space. Okay? Because this is in essence just a dual form of Bourgain's lambda Q estimate. And then we have the corresponding result when P and Q are between 1 and 2. Okay? So we proved it directly, but it follows very nicely from the annihilation inequality as well. Okay, and also just to remind you that whenever we have an uncertainty principle, we have a corresponding result for signals. So in this case, what I've simply done here is combined all the recovery results into one. So the one you haven't seen before is the last two. So if the size of e to the 2 minus p over p times the size of s. So s is the set of missing frequencies, e is the support of the signal. If this is less than n to the d divided by cpq squared, and you have this factor 2 to the power of 2 minus p over p. That factor simply comes from the fact that when you have that signal g, if you cannot do the exact, if you assume that you don't have exact recovery, then the support of f minus g is at most twice the support of f, and the various factors of 2 that you see come from that. Okay? So once again, we can get exact recovery results from restriction results or from annihilation inequalities results, and they are less stringent conditions for a generic choice of lost frequencies. Okay, so let me give you a few consequences of the annihilation inequalities. So Donoho and Stark proved in their paper that if f is a signal and E and S are in Z and D such that f is concentrated in E at level epsilon E in the following sense, so the L2 norm of f on E complement is bounded by epsilon times L2 norm of f in the whole space. This is a normal definition, the usual definition of concentration. And f hat is concentrated on S in the same sense, with constant epsilon S, where both epsilon E and epsilon S are, of course, less than 1. Then we can deduce from the annihilation inequalities that epsilon E plus epsilon S is bounded from below by 1 minus the square root of the size of E times the size of S over n to the d. So this is the Donoho-Stark result, okay? And the following is a direct consequence of our annihilation pairs inequalities, and I'm going to compare it to the Donoho-Stark estimate in a moment. So f is a signal, f is L2 concentrated on E, and f hat is L2 concentrated on S, so with constants epsilon E and epsilon S respectively. And suppose that S is in Z and D, satisfying the PQ restriction estimate with norm CPQ, then epsilon E plus epsilon S, these are the concentration constants, are bounded from below by 1 over 1 plus 1 over the 1 minus the square root of this quantity that we get from the annihilation inequality. The only thing I want you to notice about this is that even in the case when we take the L1 restriction theorem, which always holds, this is a slight improvement in Donoho and Stark. The slight improvement comes from this 1 plus. I'm not making a big deal out of this. This is just meant to illustrate the efficiency of annihilation inequalities, right? I don't think that this moves the needle as far as applications go. I'm not trying to overstate it, but it doesn't.
So without the 1 plus, in the case that C1Q is 1, it's the same as the Donoho
Stark. Yeah. So this is a little bit stronger in the sense that 1 makes the
Always distance 1 minus the square root.
I'm sorry?
It's always a distance 1 minus the square root.
Yeah. All right. And so how do you prove this? It's completely direct. So L2 norm of F is bounded by the annihilation constant, whatever it is, times the L2 of E complement plus the L2 norm on S complement of the Fourier transform. We apply the concentration assumption. This is bounded by the annihilation constant times epsilon E plus epsilon S times the L2 norm of Z and D. We cancel the norms and we get the inequality. This is elementary school level deduction. Okay, from this. Nevertheless, it's again an illustration of the power of the annihilation inequalities. You get lots of things for free. Okay? Yeah, so you get the epsilon E plus epsilon S is bounded from below by 1 over the annihilation constant. Okay, so the smaller the annihilation constant, the more powerful this result is. So in the 7 minutes that remain, what I want to do is just have a brief discussion of what is to me one of my favorite topics. I just chose not to put too much focus on it in these lectures, and that is what happens in the arithmetic setting. What happens if you assume that n is prime? Because when n is prime, algebra comes in, and unlike most analysts, I love abstract algebra, and so there's some very, very interesting things. Okay. So in 2006, Terry Tao proved that if F maps Z mod P to complex numbers, P prime, by the way, when I say that P is prime, I'm always talking about odd primes. I don't believe that 2 is a prime, they're either 1 to B, and they're simply wrong. I mean, they're entitled to their opinion, but they're wrong. Because when I started working on finite fields, like the first 3 or 4 papers I wrote, the referee wrote, I told you in the previous 2 times, apparently it was the same referee. But your result is false when P equals 2, and here's an example, right? So it took me a while to get it. Okay, anyway, so then I just decided 2 is not a prime anymore. So F is supported in E, and F hat is supported in S. Then you have the size of E plus the size of S is bigger than or equal to P plus 1. Okay, this is sharp, of course, because you can just take a second. Right? And so the key element is what I mentioned before. It's one of the most gorgeous theorems that mathematics ever produced, and this is theorem due to Chebotarev. Am I pronouncing it correctly? It's Chebotarev, right? Okay. And which says that if A and B is in ZP, and the size of A equals the size of B, then if you take a determinant of a minor of the Fourier matrix, so where X is in A and M is in B, this determinant is not equal to 0. So chi of T is the usual character over Z mod P. Okay? And Roy Meshulam wrote just a really beautiful paper where he used Tao's result in an iteration argument where he showed that if F maps ZPD to complex numbers, so a signal in ZPD, and F is supported in E, and F hat is supported in S, then if J is between 0 and D minus 1, you have the following version. You have P to the J times the size of E, plus p to the d minus j minus 1 times the size of S is bounded from below by p to the d plus p to the d minus 1, which of course reduces to Terry's estimate in 1. Okay? So what I'm going to do is I'm just going to give you a sketch of the proof of this result, and then I'll mention some other higher dimensional arithmetic results. So the first, you observe that if p of x1 through xn is a polynomial with integer coefficients, sorry, and if p of omega 1 through omega n is 0, so here omega 1 through omega n are roots of unity modulo p, then p of 1, 1, 1, 1, 1, etc. 1 is equal to 0. Okay? So this is just beautifully simple. Imagine that n is equal to 1, right? And p of omega is 0, and omega is a root of unity, right? Then p must be a multiple of the minimal polynomial of the primitive root of unity, which is just 1 plus x squared x to the p minus 1, and you're done. And how do you do this for n variables? You guessed it, by induction, in one line. Okay? And so how did Terry use this? By the way, there are many proofs of Chebotarev's theorem, and they're all really wonderful in their own way. But what Terry's proof uses the least algebra. Basically, this is the level of algebra that he uses. There's no more. If one is willing to use a bit more, then you can shorten the proof. And you can also cut down on the ugly calculations. I will tell you where the ugly calculations come in, though I'm not going to carry them out. Okay. So we need to show that, so you take omega j to be e to the 2 pi I x j over b, and we must show the determinant of omega j to the c case, where j and k are between 1 and n, is not 0. Okay, so what do? We define the determinant, where we put in zj's in place of the omega j's, and we simply, okay, so I think the next line is simply obvious, because you are going to get 0 if zj equals zj prime. And then you have p of z1 through zn in front. And then Terry simply notices that if we show that p of 1, 1, 1, 1, 1 is not 0, then we're done. Okay? And the way he shows that p of 1, 1, 1 is not 0 is by constructing just the right differential operator that reduces this to the Vandermonde determinant. Okay? How he guessed that the differential operator has to be exactly in that form, I don't know. I've stopped asking myself these questions a long time ago, but this is the type of a calculation that's used.
Okay, 1 second. On the previous slide, the main thing was the conclusion that P1111 is 0.
Right.
And here we prove that P1111
is not 0,
So
which means that since the since the omega j's are distinct, we know the determinant cannot be 0. Because the second factor also cannot be 0. It's an extreme proof of Chebotarev. It's a proof of Chebotarev. It's extremely clever proof, except what is being buried here is a really, really nasty algebraic calculation. The reason I was up until 4 a.m. is because I checked the calculation, because I figured I should check it once. And it's correct, but it's nasty. I'm sure that Terry can carry it out in a simpler way, but.
So it's like crazy Vandermonde.
Yeah.
We can call it crazy Vandermonde lemma or something.
Exactly. I mean, look, in retrospect, everybody's clever in retrospect, right? So we know that Vandermonde's determinants are non-zero, so we know that we need to work towards that. And once you know what differential operator to use, then you can say that it's obvious, but no, it's not. All right, I guess I'm out of time. Would it be a crime if I took 3 more minutes? No. I mean, don't tell Sog. You told me never to do that. How many years ago? I don't want to count. It's 31. Okay. All right. So, first of all, proof of tau is uncertainty primitive. principle. Maybe I'll do that and I'll just cover the higher dimensional stuff tomorrow. Okay, so how do you prove Tao's uncertainty principle? This is actually not the way he did it, but it doesn't matter. It's all equivalent. So for every m not in S, you have 0. Fourier transform is 0. So you have summation of chi of minus xm f of x is 0. And this gives us p minus the size of S equations and the size of E unknowns, where the unknowns are the values of f of x over x and E. Okay, by assumption, p minus the size of S is bigger than or equal to the size of E. I love it when well, in America it's like high school, but in the old country it's second grade mathematics. So when p minus the size of S is bigger than or equal to the size of E, so we have at least as many equations of variables, right? We can remove extra equations, so we get a square matrix. And since the determinant is not 0, this implies that f of x is identically 0 and we're done. That's it, that's the level of mathematics. And on this note, I'm going to stop, and I will finish up tomorrow in Euclidean space.